Okay, so as I mentioned in the other video, I'm going to talk through the first practice problem that we did on the board, and this is a little higher quality. And then I'm going to go through the next two practice problems. So here what we did, this is our first look at an ice chart, and we were given the initial value of carbon dioxide that was in the solution, and we were told that at equilibrium, the value of carbon dioxide was 0.125. Now, often in some of these questions, we're not going to be told the equilibrium concentration. We're going to be solving for what that may be. But in this first example, we're given both this value. We were given it in moles and volume and calculated the concentration, and this value. Creating this equilibrium expression where our changes here are variables that always have these coefficients in front, we're able to solve for the KEQ value, knowing that the 0.125 moles is the value we can use to solve for x, which is that variable within the expression. Solving for x using the expression for the equilibrium concentration of carbon dioxide, we get that x is 0.25 moles per liter, and then because the x value is exactly the same as the concentration of oxygen gas at equilibrium, we know that 0.25 moles per liter is the oxygen gas, and we can plug that value in for x and solve, and we get our KEQ for this expression is 4. Problem 2, we're given this reaction. I've written out the KEQ expression, and we're going to fill in the ice chart. Now, as I said, we're asked to calculate the initial value of this value. I'm going to use A as my variable, and then we're told that initially none of the products exist in the reaction, and plug in that whatever our A value is changing at a rate of minus 2x, and NO at 2x, and Cl2 at just x. These give us our expressions for each species at equilibrium. And we're told at equilibrium that there are 0.5 moles of nitrogen monoxide in a 2-liter vessel, meaning we have 0.25 moles per liter, which is our equal to 2x, given this value here. We solve for x, and that is 0.125 moles per liter. We now know x, and we can find A using our KEQ expression. So we're going to plug in these values. NO squared is 2x squared, so that's 2 times 0.125, so it's 0.25 squared times 0.125, all divided by A minus 0.125 whole squared. And we're given that our KEQ is 3.5. So we can rearrange this equation and take the square root, so that we have, so let's write it as the square root of A minus 2 times 0.125 is 0.25, and that's 0.25 squared times 0.125 divided by the KEQ, which was 3.5, and take the square root of one side, you need to take the square root of the other. Here we're going to, this squareds cross themselves out, so I didn't include the squared from this equation when I rearranged originally. That's important. So A minus 0.25 equals, if you do all of that, you're going to get 0.047245. 0.047245 plus 0.25. Your A value here is going to be 0.2974 29724 moles per liter, which we're going to round to be 0.30 moles per liter. And that is the practice problem 2. So the difference here between the first one is you're given the equilibrium concentration of one of the products and you need to solve for that initial value. So for practice problem 3, I'm going to just carry my notes here for this one so that I don't keep looking down. We're given that 0.15 is the initial concentration of both the ethene gas and the bromine. And we have none of our product to start. Meaning our change for all of these values, because we have no coefficients, is just plus or minus x. Writing out our equilibrium expression, we'll see that both of our reactants will have the same expression at equilibrium. So that if we take our equilibrium expression that we have here, and I think it was 3.45 was our equilibrium constant, and plug in our values, we get that 3.45 is equal to x divided by 0.145 minus x whole squared. This means we're going to need to use the quadratic formula to solve for x. And I've done that, so let me write the rearrangement here would be, you have negative 3.45 x squared plus 2.035x minus 0.077625. So all I've done here is rearrange this formula to get none of the terms on one side to be able to have your A, B, and C values to plug into that quadratic formula. So plugging it in, you're going to get that x equals negative 2.035 plus or minus the square root of 2.035 squared minus 4 times negative 3.45 times negative 0.077625 all over 2 times negative 3.45. Okay, that's our quadratic formula. You're going to get two answers here. So I'm just going to write out the two values. You're going to get that x equals 0.04099 and that x equals 0.54886. So you're always going to get two x values because it's a quadratic formula. Often you'll have one positive and one negative value, where clearly it is not the negative value. If you had a negative x, then you would be adding some of your reactant out of nowhere. You would just be creating matter, which doesn't happen. When you have two positive values, you have to look at your initial concentration. Because this value is smaller than the 0.15, it can be subtracted from that value to get a positive concentration. You can't take away more than what you started with. So you can't have 0.15 minus 0.54886 and get a negative concentration at equilibrium. So you will always get two answers, but one of them will always be the only one that works. You won't have the situation where the quadratic formula gives you two answers that would be correct for x. So now we know that that is our x. We are asked for the equilibrium concentration, which is just x. So your final solution to 3 significant figures is 0.0410 moles per liter. And that's 3 different ways to look at some of these ice chart problems, and we're going to do a few more next week.